when I ask you this trivial question, how many conscious beings are in this room? You can't give me a scientific answer. He wrote it down. This is the mathematical law of conscious perception. So you probably, hopefully, see a traffic scene, and once in a while I present little flashes. Why am I doing that? Well, I want to convince you that seeing is not as trivial as you think it is. Because what is actually happening is I'm showing you two images. And there's a big change between these two images. They're separated by the flash. But even as you look at this image, you might be quite convinced that you see everything and nothing is changing. And I'm telling you, each time there's a flash, there is something changing. It's right here. So each time there's a flash, we're changing that. Why am I showing you this? It's to rob you of a notion that we all were born with, that we call naive realism in philosophy and the science of consciousness, which is that you think you see the world. And that seems to be a valid, pretty good assumption, because we're not bumping into doors, we're not getting hit by cars, so our vision seems to be quite well. Now, as you proceed through high school, you realize that you do not really see radioactivity, and that might kill you. There are things out there in the world that you cannot see. So you are not perceiving, seeing, consciously experiencing the world as it is. So this idea is wrong. And as you learn more about vision, you realize, for example, that the color green that you think you see does not really exist in the real world. Yes, there are certain wavelengths that you tend to see as green, but there are people that do not see the color green as green. It's not an objective color. It is something that you experience that is only loosely linked to the world. And at that point, of course, as a high school or college student, you will say that makes sense because the way that I perceive the world is mediated by this, the nervous system, in particular, my brain. So we have our eyes, we have a brain, and as somebody put it so eloquently on Reddit, no endorsement, the nervous system, that is us. The rest of the body is an organic spacesuit worn by this creature to live on this particular rock revolving around a star. It's very rare. But what this person is getting at is, of course, what I'm getting at, which is that when we talk about conscious visual experience, we seemingly talk about physics at first, light in particular, making it onto your body, your eyes in particular. And there are a lot of things are happening. Phototransduction, photoreception, and then that makes it through the brain. And somehow, at the end of all of this, you are seeing the color green. So the first thing I want to do is delineate what we call sensation in science. Sensation is that information is registered, like your computer does, your iPad does, an amoeba does. Perception is that you see the color green. That is more than just registering. And usually, when we think about that, it's like, well, then something somehow is happening in the brain that must give rise to this conscious experience. What do we learn about what happened? So the first thing that you learn is that, well, through the lens, visual images get distorted. They end up as two-dimensional, again, non-colored images, even though the world is three-dimensional, on the back of your eye. You have blood vessels in front. You have axons in front. You have ganglion cells in front. All of this stuff is incredibly destructive. You have tiny receptive fields that neurons only respond to. The images flip left and right and up and down. You have a blind spot in each eye. But somehow, okay, that's a starting point. It makes it through the midbrain, the thalamus, the lateral geniculate nucleus, to the primary visual cortex. And indeed, what we find there is that neurons, they don't respond truthfully to the world, in that if you look at a person, half of the primary visual cortex will respond to their mouth and nose. But they do respond in an orderly manner, that neurons that sit next to each other, they respond to neighboring things in the real world. It's a mosaic, all right, but it seems to be a map of the real world. Now, this doesn't tell you, again, why you see what you see. And you see it not upside down and flip left and right. And you do not see too much of the nose and the mouth. So this is where we usually keep going. And we say, yes, okay, so V1, that is maybe just the first part where information arrives in the brain. And then these neurons, they talk to all of these other neurons. And you move forward up to the dorsal part of the brain. And we say that is the where stream, where neurons are really interested where things are, or if they move or change. Or they move towards the lower part, towards your mouth, in the temporal lobe, where neurons seem to be more interested in what you do. And then indeed we think that this is a cascade. This is a process like a ladder where neurons respond, they do something, a computation. They then move on to a second computational process. And they do this and do this and do this to all these areas. And if we measure the times, the average times or the initial time after we turn something on in the eye, we see it takes longer and longer. So that seems reasonable that somehow in your brain you have this volley of activity that starts in the eye when photons are registered, and then it moves forward. And then somehow again, you see the color green. And at that point, this is usually where these scientific lectures about vision science or the neuroscience of vision end. We teach that each of these areas has a job. So some of these areas, they respond to motion very well, others to color very well. And that is a beautiful model because this is how we learned that conveyor belts have become so effective. If you have a factory where somebody just always puts the left front wheel onto a car and another person the right front wheel, the whole car can be put together much more quickly. This is what the brain is maybe doing. It's a Fordian factory where each area has their own little job. Again, leaving open the question. If color is over here, form is over there, shape is over there, depth is over there, why do you see all at the same time? These neurons are not even directly connected, and each neuron is only responding to a part of the field. Now, to make matters worse, everything I told you is completely irrelevant to how you see anything. Why? That's because everything I told you also happens when we knock you out. We can do everything that I just told you about. We can measure where color is mostly processes, form, and so on. And then we do an MRI scan while they sit in an MRI machine. And then we do the exact same thing when they're under general anesthesia, no consciousness whatsoever, same as brain death or coma, and we find the exact same thing. All of these neurons, they do the same thing whether you see something or you see nothing because you are deeply asleep. And that is not surprising because everything I told you, as I said, are computations. And there's a general problem with that. So for that, I want to briefly show you a video from YouTube.
I will be drawing a number from 0 to 9 onto a grid divided into 25 squares, or pixels. Now, each person, or neuron, will receive one pixel. If a neuron receives a pixel with writing on it, it will fire. The V1 layer identifies pixels in the retinal layer that form particular lines in the number, and the V2 layer identifies particular combinations of lines from V1 that form angles. V4 neurons will fire when their assigned combinations of angles have been detected. Our IT will consist of 10 neurons representing the numbers 0 through 9. They will be looking at neurons in V4 and will only fire when their corresponding neurons fire. Our human brain will have a couple hundred people spread out in 5 layers across half a football field. Every single participant will be assigned to only react to certain neurons in the layer ahead of them. And it's complicated, so their positions on the field had to be carefully chosen so that every neuron has a clear line of sight to the neurons they are connected to.
I want to take a quick break here. Everything that you're seeing is to take humans and turn them into neurons, because if you think that neurons compute, people can do that too. So what neurons get are input signals from other neurons, and then they integrate and fire. So they sum them together, they see if that exceeds a certain threshold, and then they get active, and they tell other neurons. So we can do this with people. You can sit them on a soccer field, and then we can let them do what we think our nervous system, all these visual areas are doing. So in particular, that you have tiny little receptive fields, you only see a part of a number. It makes no sense to you what number it is. But you tell other neurons, other players on the soccer field, and then they do, and so on. And at the very end, if we have a V2 and V4 and all of these areas, somebody should get a flag and say, this is the number 8 or the number 7. Does that make sense? Let's see if this works.
There it is. Now it's time to distribute these pixels to the photoreceptors in the retina. 25, 24, 19, 13. All right, I have distributed the input to the retina layer. Think. And they're off. The retina layer has fired, passing off signals to V1. V2 sees V1 firing and also fires, cueing V4 and IT. All right, Chris, what numeral do you think I drew?
I think you drew a 3.
The numeral I truly drew was a 3.
We can register information and put it together, and the brain seemingly does it. Those are computations. But where was the seeing? And I think this is why I have to talk about AI. If you learn about it, you learn that it is just mathematics. Indeed, what ChatGPT is doing, I'm going to show you in another brief video.
If you look under the hood of ChatGPT, you won't find any obvious signs of intelligence. Instead, you'll find layer after layer of compute blocks called transformers. This is what the T in GPT stands for. Each transformer performs a set of fixed matrix operations on an input matrix of data, and typically returns an output matrix of the same size. To figure out what it's going to say next, ChatGPT breaks apart what you ask it into words and word fragments, maps each of these to a vector, and stacks all of these vectors together into a matrix. This matrix is then passed into the first transformer block, which returns a new matrix of the same size. This operation is then repeated again and again, 96 times in ChatGPT 3.5 and reportedly 120 times in ChatGPT 4. With a few caveats, the next word or word fragment that ChatGPT says back to you is literally just the last column of its final output matrix, mapped from a vector back to text. To formulate a full response, this new word or word fragment is appended to the end of the original output, and this new slightly longer text is fed back into the input of ChatGPT. This process is repeated again and again, with one new column added to the input matrix each time, until the model's output returns a special stop word fragment. And that is it. One matrix multiply after another, ChatGPT slowly morphs the input you give it into the output it returns. Where is the intelligence?
I think that's a good question. Everything I showed you is actually just linear algebra that you know from high school. In particular, it is matrix multiplication. You take an input, turn it into a vector, you multiply it with a bunch of matrices, and you get an output vector. If there's not even intelligence here, then I really question that there is something resembling consciousness, experience, as you see the color green. And the connection is, of course, that in both these cases, we looked at calculations, computations. So for the remainder of this talk, I want to convince you that that, of course, cannot explain the other. And that is because we've learned long ago that complex behavior, cognition function, can happen without conscious experience. So you see this right here. This is a senator who has a frontal lobe seizure. He's still standing. This right here is what we call persistent vegetative state. Her life support was turned off, but she's responding. Now, the opposite is also true. You can have conscious experience without complex behavior, cognition, or function. And so this is one famous example that people learn about, somebody that has a rare disorder that's called locked-in syndrome, where the body is completely paralyzed, but the mind, the consciousness, everything is working just fine. And the reason that we know, and the reason that we can make out what this person is thinking and saying is thanks to modern technology that we can read out their brains. But it's even more pedestrian than that. So visual experience without function you're quite familiar with. We call this a dream, and you do it every night. The reason that there's no function is that you have a nucleus in your brainstem that makes sure that you don't move. If we destroy that nucleus, for example, in cats, which were experiments done in the 60s, these cats do act out their dreams. They are sleepwalking, and that's because they are experiencing something, and the only reason that there's no behavior is because they're completely paralyzed. In fact, that paralysis, the fact that you cannot move a single muscle on your body, is how we know that you are in dream sleep. So there's quite a bit of visual experience without behavior, and the inverse is also true. So a few patients that had lesions to the primary visual cortex rendered them blind, but not because primary visual cortex is where consciousness is produced or located, but because it's like the eye, it has to feed the information on. And a couple of years ago, this video made the rounds on the internet of a person that is completely blind because that person has no primary visual cortex, but that person, they can walk around obstacles just fine, a phenomena that we know since several decades that is called blindsight, where blindness refers to the fact that there is no seeing, and sight, again, sensation, that the information is properly processed. And this is, of course, a major problem in neurology. So I'm telling you that consciousness is actually more than responding or even being aware of the world. Somebody who is heavily drugged out may do neither, but they are still fully conscious. So there seems to be a problem to go from behavior or function to consciousness as a difference between procedural and structural descriptions in science. And it was first found by Noether. one of the greatest mathematicians of last century, who was very much interested in physics. And so what she found and proved in her theorem, I would call a concrete mathematical example of the broader principle that processes only explain other processes. What I mean by that? So I don't want to go too deep into formalism, but what she showed is that certain physical properties are invariant under transformation, but that does not contain no information about the origin of let's say, electric charge. So in other words, it doesn't tell us what electric charge is, nor where it is coming from. So the mechanistic laws of physics that are concerned with procedure, they describe transformations and conservation, but not states of existence, such as electric charge. So electric charge is conserved, for example, under gauge symmetry when it comes to quantum field theory, but that doesn't tell us why charge exists or what it is. And that doesn't make charge metaphysical or supernatural or mystical either, because we do have mathematics to describe what electric charge is. It's just different math. It's math for intrinsic properties, just like the intrinsic property that you see something. And that math is usually fields, rings, groups, or pedestrian numbers. But my whole point here is something more simple. It says that how something changes does not fully define what something is. In big words, we say that how something changes is an intentional explanation, whereas what something is an extensional explanation. But to put it again more simply, you of course know that you are much more than what you do. What you do doesn't fully define who you are. In fact, you have to be first before you can do anything. If anything, the state of existence, being, is primary to doing something. And we can push this. So how something evolves, same thing, how something changes, cannot explain why something exists. And so I argue for the remainder of my talk that is why computations and similar processes cannot explain why consciousness exists. And that is why this was so puzzling, what I just showed you. When I said, look, we know what the brain is doing, and then we do it on a football field, and consciousness all of a sudden is gone. Is it hopeless, though? Not at all. Let me show you what I think is really going on. And I will resort to physics again. So let's look at this beautiful Renaissance painting. And I'm going to ask a few questions. So for example, how many oxygen molecules are in this room? You can give this image ChatGPT and it will answer. It will say, well, the room seems to be roughly this size. Air has about a quarter oxygen. At standard temperature and pressure, we can then compute how much oxygen is in this room. And that is thanks to three, here comes, laws of nature, mathematical rules, equations. The ideal gas law, Avogadro's law, and the laws of thermodynamics. Now, I hope we all agree that this is good science. This is as good as science ever gets. That we ask a question such as, how much oxygen is in this room? And thanks to these laws of nature that are immutable, unchangeable, always true, inarguable, and precisely true, we can give a precise answer. That is, of course, why, as scientists, we like mathematical descriptions of the world. And the first scientist who came up with it put it, of course, the best. The book of nature is written in the language of mathematics. That is why, as scientists, we should embrace mathematics. Now, why mathematics best explains the world? I do not believe that we have an answer. But it is so. And then there's a problem with consciousness. So, of course, mathematics describes much more than physics. But out of everything that mathematics describes, it seems that physics, chemistry, biology squarely sits inside because it can be fully described with mathematics. So you might have heard this quote by Theodosius Dobzhansky. Nothing makes sense in biology except in the light of evolution. And I believe there's a lot of truth to that. But I want to rephrase that. Nothing makes sense in science except in the light of mathematics. That's because the book of nature is written in mathematics. And if you're still unconvinced, this is the famous Lagrangian of the standard model. So what we found, for example, is this right here predicts the G factor with 13 decimal points. And we find it to be exactly this case. That is an unbelievable precision. That's remarkable. Why? Because these mathematics, a lot of this, we found hundreds of years before we knew what the G factor is. So it seems that us humans, somehow we can come up with these equations, with these laws, these mathematical structures or objects. And they seemingly explain the universe. In fact, they also explain computation. So here's a good example. This is what you might have learned before, that when it comes to computations, especially in the nervous system, it has been proposed that there are 3 levels that we can describe things at. The implementation, how the computation is performed physically, the what, the algorithm, and then lastly, the computation, which is even more abstract, the goal. And so let me show you a very famous computation, one that might change the world because it runs on quantum computers and we had it there fast. This is a quantum computer. They already exist. They're still very primitive, but we can use them. This right here is the algorithm that I want to introduce. And if you're interested in quantum computers and you're an academic, you can use them for free. They're not very good, I have to say, but you have to learn these graphical programming languages. They're not that hard either. They're actually quite fun. And then lastly, the actual goal, the computation right here, is a database search. So what I'm showing you right here is what's called Grover's algorithm, and it's one of just a handful of algorithms that we know will perform faster on these machines than on the other machines that we have. But it's quantum physics, so in fact, Grover's algorithm is also just this one line of an equation. This right here was not a foundational basic explanation. It's a level too high. I can reduce it to mathematics because, again, it's mathematics where we have to explain everything. Now, this is where I usually get a lot of pushback. The first is I don't like math, and I don't either. And it's because I used to think math is this, whereas math is more like that. I was scared of math because the way that we teach math is there's one correct solution. I know it, you don't, and you have to find it. But math is not a competition. It's not even a competitive sport. Math is actually much more than that. Math is finding structure. And most of us like that. If you like puzzles, you like math. We literally call that figuring things out. That we provide structure to the data that we have. Now, at this point, I sometimes hear the following, but you still have to explain that math is something that us humans do. We came up with the crazy concept that you can take the square root of -1. How is that possible if any negative number, if I square it, is positive? How can you take the square root of a negative number? And yet, without that, your iPhone, your computer, this laser pointer wouldn't work, wouldn't even exist. Hundreds of years before we did that. But these people would argue math is just a language. Well, not for your brain. So what we can do is we can show people language and we can show them mathematics. It's entirely different parts of your brain to get active. So at least your brain does not believe that math is language. Now, the next one that I often get is that, well, math is oversimplification. I already showed you there's nothing more precise than it, but okay. And that quote, I actually had to look for many, many years until I found it. It comes from an old statistics textbook. And let me tell you, statistics in most universities is not housed in the mathematics department. That quote is, you might have heard it, all models are wrong. Well, that may be true for statistical models, but it's certainly not true for mathematical models. Let me show you. This right here is what we call a 1 meter. It's a model of 1 meter. It's exactly 1 meter. Why? Because we call a certain length 1 meter because of this meter. So what happened is people had to come up with a unit of length. So back then, in France, in Paris, some people made a piece of metal, and they said, that's 1 meter. And then everybody had to go measure it, go home and say, folks, that's 1 meter. That's how we have 1 meter. That's a model, of course. A meter is just something abstract. Is it wrong? All models are wrong? No, clearly this is correct. It's a correct model. That's why it is the same thing. It's a one-to-one referent. A one-to-one model is the real thing. It's not wrong. It's entirely correct. And you know that because if you copy a file, you create a one-to-one model and you know it has a problem. See, then at this point, sometimes I get another pushback, which is, yeah, but science never tells you the truth. While we have these mathematics, science is still relative because as science progresses, we're learning new things. And that's inarguably true. Of course, science never claims to know the truth. In fact, there's a deeper problem, which is that in mathematics, we have to make first some assumptions that we can't prove in the first place. But I think this is also a misunderstanding. So if we look at physics, this right here is how we learned what the atom is made out of. And quite surprisingly, it wasn't until around the First World War that we had first ideas. And you probably learned that there's a nucleus and it contains neutrons and protons and there's electrons flying around and there's forces in between those. And so indeed, if you look at the mathematical structure, I'm trying to make it easy, people figured out very early on there's a proton, there's an electron and a force in between. And then we figured out, well, there's not just protons, there's also neutrons. So that took until the 1930s. And then we learned that, no, it's not a force in between. It's actually an exchange of a photon that is keeping the electron close to the neutron and the proton. And then we learned that the proton and the neutron are actually made of smaller particles. We ran out of words. We called them quarks after a German dessert dish. And so then we learned that, okay, the nucleus is made out of these quarks, and then we learned that these quarks, they are held together with other quarks that they exchange. And since the 1970s, we have learned nothing new. Now, I want to draw your attention to the fact that we have red, yellow, blue, red, yellow, blue, red, red. So while we are adding detail, the initial idea was never changed. So science does not progress revolutionarily. Science tends to progress more as images are sharpening over time. We're learning more, we're improving, we're adding detail, we're getting more and more precise, but the fundamental mathematical structure uses to be retained. And I think I can make the case the same is true for neuroscience. So for example, Cajal was the first who said that the brain consists of individual units, the neurons. Then we learned that there are two types of synapses in the 1950s, thanks to electron microscopy and some other techniques. And then lastly, we made a little bit of a U-turn. And now we believe that there are also neurons that are directly connected. We call those gap junctions. Here's another example, if you don't find this satisfying. So we learned in the 1800s that there are electric nerve signals. It took a while to realize what electricity is and that the brain does it. In the 50s, we learned that those are action potentials. In the 70s, we finally realized how this works with ion channels. And then in the 2000s, we learned, no, it's actually not just happening on the axons, it's also happening on dendrites. So again, it's like the picture gets more and more clear. So I hope I could make a case that once we hit a mathematical theory, a mathematical structure that explains nature, we seem to do pretty well. And at that point, it seems that we're making progress because then we're just getting better and better and better. So how does it work for consciousness? So let's go back to this painting that I showed before. Now I want to ask another scientific question. How many conscious entities are in this room? Now, I emphasize it's a scientific question. I don't want you to look at it and just come up with an intuition. I want you to give me an answer that's as precise as the oxygen molecules that I said before. Okay, so is it the same as the number of humans? What about the baby? Is it conscious or not? What if the baby's sleeping? Is Rachel sleeping? What if she's dead? Are there animals around? Are they conscious? Do dogs count? If there's mice we can see, a cockroach, are they conscious? The amoebas in the side. It seems that we're hopelessly lost. While it was easy to tell how many oxygen molecules are in this room, think about it, something that you can't see and count. When I ask you this trivial question, how many conscious beings are in this room? You can't give me a scientific answer. That's a really simple question and no scientific answer. And that's because we don't have a really good theory. In particular, we don't seem to have a good mathematical theory that gives us laws, equations of consciousness that could answer that, just like Avogadro's law. So it seems, and this has been the assumption for much, at least, of Western academic thought, that while science, the book of nature, rests inside mathematics, consciousness is different. Consciousness is not part of math. We cannot express consciousness mathematically. If you tell me I fell in love yesterday and I say how much, 5 or 7, you laugh at me. And that's a problem, of course, because we do know that consciousness is real. You know that you are conscious. And so it leads us to say these neurons are active. You see the color green, and in between there's something that's not science, not math, not computations, as I showed you. And yet you're conscious. Well, that is a very unsatisfying state. And what I want to show you is it's wrong for a very simple reason, that we can move conscious experience right inside this ellipse of mathematical space. No problem. And that is very important because we are increasingly facing questions such as, is a fetus conscious and when? We found people that are diagnosed as unconscious, but when we put them in an MRI machine and we say, imagine you're playing tennis, or imagine your mother calling your name, we see different activation in the brain. And if we do that with conscious people, it's the same activation. In fact, these people that have been diagnosed as unconscious, and the question is, should we take them off life support? We can ask them questions. I will tell you 5 names, and when it's your name, or when it's your wife's name, or the name of the current president, imagine you're playing tennis, and then you see activity in the area that is processing space. And lastly, and that's maybe the most scary, is that when we put people under, we also give them drugs that make them not move so that you don't fight the system that makes you breathe. Worse than that, we also give you drugs, so it's a side effect of some of them, that you do not remember what happens when you get these drugs. They're like roofies. So that raised the concern. Maybe some people are fully aware doing surgeries, and this is what we call intraoperative awareness. And so there are studies, and we do find there's evidence that that indeed exists, that surgeons believe that the patient is unconscious, the patient cannot move, the patient is experiencing the entire surgery and then will forget about it afterward. And then maybe you find PTSD or something else later in these people's lives. And nobody has a clue why. Again, let me emphasize this is really rare, but it is because we as neuroscientists are failing. That we cannot look at a brain that we know is producing consciousness or not and tell the difference because we do not have the science, the mathematics, the equations, the laws of nature that allow us to do this. Or do we? This is where the good news comes in. So people have thought about this for a long time, and it's a little bit forgotten knowledge. That's why I'm so agitated and want to tell you. So one idea is if I think about the physical world like stimuli, and I think about your conscious experience, is there not a way that we can link this mathematically? And I told you it seemed that no. If I ask you, how much in love are you? You would not say 5. But let me make this following thought experiment with you. Just imagine that I would blindfold you here in front, and you would stretch out a hand. And I would put a piece of paper on. And so you're blind, you don't see anything, but you feel that piece of paper. Can you imagine that? Okay, so now on that piece of paper, I add very silently, without you hearing that, I add feathers. Do you think that at some point you feel that this becomes heavier? Might be a certain number of feathers, but at some point you can tell, whoop, I know you're adding something and I can feel the difference. But if I add just a little bit of a feather, could you imagine that you don't feel anything? Okay, so now we're talking numbers. So we went from 0, I feel no change, to I feel a change. And I can take the weight, that was your 0, and then the weight where you feel a change. So now I have 0 perception, 1 perception. And I keep going, right? So now I say, okay, so now you feel that new weight with the feathers, and I add more and more and more feathers. Do you think at some point it will feel heavier again? I make it heavier, right? So I'm adding a little bit of feathers, so it might feel the same way. So you're still at perception 1, and I'm adding more and more feathers. Now you go, I feel a difference, and you go to perception 2. So you get a staircase of 1, 2, 3, 4. So your weight perception seems to be numerical. In fact, it's integers. It's counting numbers, 1, 2, 3, and 4. And this insight was first found by this guy, Gustav Fechner, one of the greatest scientists that ever lived. He knew that this would be a hard sell to people, but he was pretty smart. So he named it psychophysics, which I think is very sexy. The whole idea was that we're taking physics, math, and we're explaining psychology, your perception with that. He was, by the way, just a graduate student when he did that. Despite the marketing that went into there, despite this huge discovery, he never got tenure. What did he find? Well, I'd wager he found what I was advocating for. He found mathematics of perception. I just gave you a hint of that, and laws of nature. So this is how Wikipedia explains it. So if you look at this versus that, I show you 10 dots and 20 dots. I give it away. You can tell that this is more dots than that. You might even be able to tell this is roughly twice the amount of dots. The difference, of course, is exactly 10 dots. 10 dots and 20 dots, 10 dots difference. Now, what happens if I show you 100 dots on top and then 110 dots at the bottom? Is it equally easy to see that there's 10 more dots? No. So it seems that even though we can measure your perception, be quite precise about it, there's something else going on here, which is that with larger numbers as a starting point, it seems that these differences are changing. And so now let's do this thought experiment again, where I blindfold you. And now you're stretching your hand out, you're blind. But instead of a piece of paper, I'm giving you a 1-gallon jug of milk. You hold that. Now imagine I put the same amount of feathers on as before, that you were able to tell the difference by weight when it was a piece of paper. Do you think you would feel that difference now that you hold a jug of milk in your hand? You probably wouldn't. And it's the exact same thing. If you start out with a greater quantity, it takes even longer until you get out of what we call the state of subjective equivalence. It is subjectively still the same, even though the physics is changing. It takes even more until you take another step and we can increase your perception. In fact, these experiments have been done. We're still doing them in the department every day. And we always find the exact same mathematical law. And you can already derive what this mathematical law is. If I plot along the x-axis how much weight or how many dots, how much physical stimulus there is, and on the y-axis, your conscious perception, it looks like that. Does it make sense? So if I go with small units, you are very good. You're very sensitive. The little I change, your consciousness is also changing. So if I show you 10 dots more than 10 dots, 20 dots, you see the difference. But if I show you 100 dots and 110 dots, you don't see the difference. That's the definition of a logarithm. And so once Fechner discovered that, he wrote it down. This is the mathematical law of conscious perception, at least when it comes to quantity. It's the logarithm. That's all that I was looking for. So what Fechner did to us is he gave us that mathematics, that science that we were looking for, where we can go from stimuli, we take the logarithm, and we get what you perceive. And as an effect, the initial project of mine, where I tried to convince you that, of course, this is funny, to say that somehow out of your neuronal activity, with something that is akin to mystery or magic, consciousness arises, it's actually much more banal, trivial, even pedestrian, that is due to mathematics. But I haven't shown you that math yet. I actually have only shown you how we go from stimulus to conscious experience. And I left this out entirely. So that would be our next lecture.
Consciousness first.